We're going to continue our study on matrices today. Now, we've talked a little bit about matrices in learning how to solve a linear system of equations, but we haven't talked much about what we can do with matrices themselves. So today we're going to focus on addition and subtraction of matrices. So matrices provide a convenient way to organize data, and it has gained increasing importance in fields like management, natural science, and social science. Typically, in terms of how we notate matrices, we'll usually call them by a capital letter, and they are classified by their size, and we would call them an M by N size matrix, where M is the number of rows and N is the number of columns. So take a look at example 1. The Easy Life Company manufactures sofas and armchairs in 3 models, A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B sofas, 5 Model C sofas, 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse. Use a matrix to organize this information. So here we're not doing anything other than trying to put this into a matrix form. We'll see later on in our last example how we can use matrix form to help us do calculations more easily. So we'll call this a matrix M, and we can simply use the chart and say we'll let each row represent the type of furniture, so sofas versus chairs, and each column will represent a model type. So we have 3 models, A, B, and C. So we have model A in the first column, sofas, that's 10, chairs, that's 15. With B, that's 12 sofas, 20 chairs, and with C, that's 5 sofas and 8 chairs. And that would be just it in terms of writing it in matrix form. In example 2, we're going to go ahead and practice determining the size of each of the following matrices. So take a look at the first one. The size, remember, is how many rows and how many columns, where M is the number of rows and N is the number of columns. So in the first one, if you count down, that would be the number of rows. So this has 3 rows, and if you count across, it has 2 columns. So we would say this is a 3 by 2 matrix. If you look at B, if you count down, there are 3 rows. If you count across, there are 3 columns. So this would be a 3 by 3 matrix. You look at C, we have only 1 row, but if you count across, we have 5 columns. This is a 1 by 5 matrix. And the last one here, you count down, we have 4 rows, and counting across, there's actually only 1 column. So this is a 4 by 1 matrix. Now there are a couple of particular types of matrices that have specific names because of the number of rows and columns that it has. So the first one is a square matrix. This is a matrix that has the same number of rows as it does columns. The second is a row matrix. It's also called a row vector. This is a matrix containing only 1 row. And similarly, we have what's called a column matrix, also known as a column vector, and that is a matrix containing only 1 column. Now, when we talk about matrices and we talk about matrices being equal to each other, we can only say that 2 matrices are equal to each other if they are both the same size and if each pair of corresponding elements is equal. So if you look at this example here, although you have the same 4 elements and these 2 matrices are the same size, they're both 2 by 2 matrices, they are not equal because the elements, although the same, are not the same in the corresponding positions. So you see how the first element in the first row is a 2, and in the second matrix, that's the same. You need that to be the case for all the elements. However, if you look at the second element in the first row, you have a -5 in the first matrix and a 1 in the second one. If those were the same, and if the second row, first element were also the same, then you could say that these two matrices are equal. But everything has to be equal, not just that they have the same elements, but those elements have to be in the same corresponding positions. Now when it comes to adding matrices, we can sum two m by n matrices x and y by summing each element in each of those matrices together. Now note that this only works if matrices are the same size. If they're not the same size, then you won't be able to add the two together. So let's look at example 3. We have a 2 by 2 matrix added to another 2 by 2 matrix. So all we have to do is add the corresponding terms together. So 5 plus -4, -6 plus 6, 8 plus 8, and then 9 plus -3, and that gives us 1, 0, 16, and 6, and that would be the sum of those two matrices. On the other hand, if you look at the second example, you'll see that we have a 2 by 2 matrix and then a 2 by 3 matrix. Now because those two matrices are not the same size, we are not going to be able to add those two together. So you can simply say that this is not possible because the two matrices are different sizes. Now when it comes to subtracting matrices, the same thing is going to be true. So the difference of two m by n matrices x and y is simply the m by n matrix x minus y, where each element is found by subtracting the corresponding elements of the original two matrices. So just like addition, only matrices that are the same size can be subtracted from each other. So take a look at example 4. So we have a 2 by 3 matrix minus another 2 by 3 matrix, so we can absolutely subtract those. So we just have to subtract corresponding elements. So 8 minus 3, 6 minus 5, -4 minus -8, and then -2 minus -4, 7 minus 2, and 5 minus 9. That's going to give us 5, 1, and 4 in the top row, and 2, 5, and -4 in the second row. For the second one, we have a 2 by 2 matrix, subtracting a 2 by 1 matrix. So in this case, we won't be able to subtract them because these two matrices are of different sizes. And since they're different sizes, we can't subtract, so you can say that this is not possible. They are different sizes. All right, take a look at example 5. The September shipments from the Easy Life Company to the New York, San Francisco, and Chicago warehouses are given in matrices N, S, and C below. Now remember, we have furniture types for the rows and the model of each type as the columns. Now we have 3 different matrices because these are the numbers that were sent to each location. So N for New York, S for San Francisco, and C for Chicago. What was the total amount shipped to the 3 warehouses in September? Well, to find that, all you have to do is add all 3 matrices together. So we get 45 plus 30 plus 22 is 97, 35, 32, and 25 is 92, and so on. And you can do that to find the total amounts that were shipped in September to all 3 warehouses. Now, it might be strange as to why we use matrices here, but matrices really are used when you're doing things, mostly when you're working on the computer and you want to store information. Then by having this information stored as a matrix, it actually makes it pretty easy to just say I want to add the amounts from New York and San Francisco, but you don't just want to have one number. You want to be able to keep track of the different types and the different models of furniture that are being shipped. And so having this data that's stored in each of these matrices, so let's say in the computer, then if you were just to call these matrices out, then you would be able to find all the information that you need. Take a look at example 6. During September, the Chicago warehouse of the Easy Life Company shipped out the following numbers of each model. What was the Chicago warehouse inventory on October 1st, taking into account only the number of items received and sent out during the month? So the amount that's received, we were actually just given in example 5, that last matrix there, with the 22, 25, 38 on the top row. And K, that's given here, this is what was shipped out. This is what they sent out during that month. So all we need to do is we need to take what they got, what came in, the C matrix, and subtract out what they sent out, the K matrix. Now again, generally you'll have all this information stored in a database, and in this matrix, you'd be able to simply say we want to subtract those two, and you can still keep track of the model types and the furniture types of each kind, and be able to see exactly how much of each type you have just looking at the matrix. So subtracting this, we end up with 17, 15, 30, and then 20, 20, 20 on the bottom. And here you can see that we are still keeping the information there. It's not just a total number of pieces of furniture, but you can read from the matrix exactly how many sofas of model type B there are after all the data has been entered for those first two matrices.